In this lesson, we're going to look at several concepts that are somewhat related: systems of equations, matrices, and linear programming. So up until now, we've been solving equations that have one variable, and we've been successful in doing that with linear functions, with quadratic functions, and with exponential functions. If we have two unknown variables, we would need to have two equations in order to solve for these variables. In general, if we have any number of unknown variables, we would need to construct the same number of equations in order to solve for all the variables. And this construction is called a system of equations. So here we have three images, and if we look at the image to our far left here, we can see that in this instance, we have two equations plotted with the blue line and with the red line, and they have a point of intersection. So I will circle that here. And that point of intersection is the place where each of these two equations share a point. And I think you'll recall we looked at supply and demand and that point of equilibrium. We also looked at break even, that point where revenue equals cost. And those two functions would cross or have a shared point, such as these two on the left. In the center, where there is no solution, we can see that the line that is drawn here in blue and that drawn in red have the same slope, and so they would never cross, they would never have that shared point. In the third instance, the two equations on the far right, they are literally the same equation. So one is set on top of the other, and they would share infinite set of solutions. So every point on the blue line would be a point on the red line. So for our purposes here in the course, we're going to only look at those situations where we have one solution. So two equations, two unknowns, and they do have a solution set. There are three ways of solving two equations with two unknowns, and it depends on the situation which one is the most reasonable. The first one is elimination, and that's where we eliminate one of the variables in order to solve for the other, and then using that solution we would solve for the first eliminated variable. The second is substitution, and this is when we would look at the relationship between the two variables, and we would substitute one of the variables into the other of the equations. And of course, few students pick this, but in fact graphing is one of the easy ways as well, because then you can simply read that shared point where the two functions cross. We would be able to share that point off a graph. So I will solve some equations with you and point out when it might be best to use elimination, when it might be best or feasible to use substitution. And I think at one case perhaps we'll do it both ways. I mean, you can choose for yourself what option you like best. So the first question, again using a system of equations in two variables, it reads: the populations of two cities A and B are projected to decline, but one population is decreasing in size faster than the other. Suppose that X is 23, corresponds to the year 2023, and the population Y in thousands of this given city in year X. So we have two equations here, which represents the populations of the two cities. The first one is 10x plus 13y equals 1,125. The second is x plus 13y equals 873. So again, in order to determine if we're going to be using elimination or substitution, I would look at the coefficients or the numbers in front of each of the variables to see if they come from a factor or multiple of the coefficient in the other equation. So I would look at 10x in the first equation and x, 1x in the second equation, and say, well, yeah, they're related by a factor of 10. So I could multiply the second equation by 10, and then I could subtract them and determine a value for y. Then I might look at the coefficients of the y variable. So I have 13y in equation 1 and 13y in equation 2. So I would see right away that I could subtract those two, the y variables, and I would be eliminating that y variable and be able to solve for x. I might also try substitution, so that's also possible. I'll do that as well and show you how that might work, okay? Because substitution works best if you have a coefficient of 1 for one of the variables, and I do have a coefficient of 1 in front of the x in the second equation. So let's have a go first at eliminating the y variable. So 10x plus 13y is equal to 1,125, and x plus 13y is equal to 873. Yeah, so equation 1, equation 2, just as they're written, and I'm going to subtract. So I can subtract the x's from each other, the y's from each other, and again the constant. So 10x minus x, that's going to equal 9x. 13y minus 13y, that eliminates the y variable. And then I have 1,125 subtract 873, that leaves me with 252. And then we know what to do next. We can divide 252 by 9. We divide 9x by 9, and we're left with x equals 28. So what does that mean exactly, that value? So we're told that x is 23 for the year 2023. So x being 28 corresponds to 2028. And it says here that you have the populations of both cities. So that tells me that in 2028, the population of city A and city B will be the same. So the value of y will be the same in 2028. And what is that value? So we need to substitute into that either of the equations to find out what the value of y would be. So let's try that. I'm going to use the second equation, because it's a little easier to work with. So we have x is 28 plus 13y is equal to 873. Then we are going to subtract 28 from 873. So we have 13y on one side and 845 on the other. And then we're going to divide both sides by 13. And we find that y is 65. And in the question, it says that the population is given in thousands. So we're looking at 65,000 being the population of both city A and city B in 2028. Now, what if we use substitution? So that was solving this set of equations with elimination. In this case, we could also solve it using substitution. So let's see how that might look. Again, we have, I'll just draw a line here, we have 10x plus 13y is equal to 1125. That's our first equation. And our second is x plus 13y being equal to 873. So if I were to take equation 2 and say x is equal to 873 minus 13y, we could then substitute this relationship of x to y into equation 1 and solve. So let's see how that would work. Ten times 873 minus 13y in brackets. I'm substituting that in place of the x. 13y is equal to 1125. Okay. Here I have 8,730 minus 130y plus 13y is equal to 1,125. Okay, so I'm going to do some subtracting here. I have 8,730, and I'm going to subtract 1125, and I'm left with 7,605 on this side. I have 130 negative and 13. So I'm going to have on the right side 117y. And now I'm going to divide 7,605 divided by 117. And of course, if I do the math correctly, I'm going to end up with the same value. I'm simply using a different method of solving. So again, the population is 65,000 in the year 2028 in both cities A and B. If we look at this question here, we're not given the equations, so we're going to have to build two equations with presumably two unknowns. We have a 200-seat theater which has tickets for sale. Adults are charged $8, children $5. If all the seats were filled, so all 200 seats were filled, and the total ticket income was $1,435, how many adults and how many children were in the audience? So we have two situations here. We have simply the attendance, and we know that the theater was full, there were 200 seats full, and they were filled with both adults and children. So if we say X represents the number of adults, Y the number of children, we can set up an equation representing the attendance. So X plus Y must equal 200, the seats in the theater. The second one represents the ticket revenue, if you will. So the second one says that adults are charged $8 each, and children are charged $5 each, and together the sum of those two admissions were 1,435. Yeah? Okay, so in this case, again, I'm going to look at our three options: elimination, substitution, or graphing. And again, I would look at the coefficients or the numbers that are in front of the variables. So in equation 1, I have 1x plus 1y equals 200. And in the second, I have 8x plus 5y equal to 1,435. These two equations are conducive to using either of those first methods, and also graphing, actually, if you want to try that as well. So I'm going to again solve this using elimination, and then I will also solve it using substitution. So in the first case, I have to eliminate either the x variable or the y. So why don't I eliminate the y variable in this case? So in order to do that, I'm going to have to multiply equation 1 by 5. So 5 times equation 1 will be 5x plus 5y equals 1,000. Then I'll just copy equation 2 as it is because I already have a 5y. Then in order to eliminate the y variable, again, I'm going to subtract. So I will have 5x minus 8x, so that's going to give me negative 3x. I have 5y minus 5y, so that will give me no y variables left. And I have 1,000 minus 1,435, so I'll have negative 435. If I divide both sides by minus 3, I will have x on the one side, on the left side, and 145 on the right. And remember, x represents the number of adults in the theater, in the 200-seat theater. So if I were to now say, if x plus y equals 200, and x is 145, the number of adults we determined were in the room, we can say that the number of children was 500. Sorry, 55, not 500. 55 children, yeah? So 55 children, 145 adults. I would probably check that as well. Multiply 145 by 8, multiply 55 by 5, I guess, for the cost for children, and just see if it adds up to 1,435. Now, I did say I would solve this as well using substitution. This is one that's quite conducive to solving with substitution. So again, we have x plus y equals 200. If I were to rearrange that equation 1, I would say that x is equal to 200 minus y, which makes sense, right? Number of adults is equal to the total people in attendance minus the children's numbers. And then I have equation 2, which was the revenue for the theater, which is 8x plus 5y equals 1,335. So I'm going to substitute 200 minus y for the x in that second equation. I'll expand the brackets here, so we have 1,600 minus 8y plus 5y equals 1,000. Whoops, I need to have equal sign up there. Equals 1,435, yeah? So on this side, I would have 1,600 minus 1,435. And on this side, I'm going to have 3y. So that's the minus 8y plus 5y. That will give me negative 3y on the left of the equation. And I'm moving that over to the right side. And 1,600 minus 1,435. That equals 165 on this side. If I divide both sides by 3, it gives me another way of showing that there are 55 children. With the balance of the 200 being 145 adults. So in these cases, please choose what method makes the most sense to you, either elimination or substitution. For this next question, we're going to explore inequalities and feasible region. So let's see what we mean by this. So whenever we have an equation, sort of y equals mx plus b, for example, we have an equal sign. So that just means that whatever is on the left side of the equality, the y, must be equal to what's on the right side of the equality, mx plus b. When we have inequalities, it means they may or may not be equal. So we may have y is greater than or equal to mx plus b. Well, we would rarely be looking at something like that. But In the case of certain conditions, for example, we might say they have to work at least so many hours. At least means they would have to work that number of hours or more. If we said, well, you have to walk at least 6,000 steps a day, that would mean 6,000, 6,001, 6,002, 7,000, 10,000, so on. Yeah. We can also have something that is less than. So you should consume less than 20 grams of sugar. So less than 20 grams would mean 19, 18, 17, and so on. Less than or equal to (20 grams of sugar) would now include the 20 grams. So 20 grams, 19 grams, 18 grams, and so on of sugar. So that value or something less, okay? We also have terms at most, right? Or greater than, I guess, greater than, right? They can work at most 20 hours a week because they're students and need to focus on their academics. They need a grade point average greater than 3.0 in order to, right? You get my point. We can also have greater than or equal to. A student must have a grade point average of 2.8, greater than or equal to 2.8. That would mean 2.8 is included, 2.9, 3.0, and so on. So when we're looking at questions in math, sometimes these words will be in the word problems or the questions, and we have to interpret them into something that is mathematical in nature, so an inequality. The question we're going to work on, I'll show you what that will entail. Let's look at this question. It reads, a college student works in both the school cafeteria and the library. She works no more than 12 hours a week at the cafeteria and no more than 14 hours a week at the library. Okay. And it says she must work at least 20 hours each week. Okay, so if we look at setting this up, let's say that our X value would represent hours in the cafeteria, and Y would represent hours in the library. And we're going to look at this no more than statement, no more than 12 hours a week. So she could work 12 hours or 11 or 10 or 9. So no more than 12. So we would represent that inequality as X, the numbers of hours in the cafeteria, have to be less than or equal to 12 hours. Yeah. Then it says here that this student works no more than 14 hours a week at the library. So the library hours represented by Y would have to be less than or equal to 14. Okay. The statement, she must work at least 20 hours each week, that would mean that the combined hours in the cafeteria plus in the library have to be greater than or equal to 20, right? So that's how we're going to set up these inequalities. So then the next thing we have to consider, and this is something that we might forget, we can't have negative hours, right? So X has to be greater than or equal to 0, and Y has to be greater than or equal to 0. That simply means in the Cartesian plane, we're going to be working in the upper right hand quadrant, the positive values of x and the positive values of y. And so what does this thing about feasible region mean? We didn't cover that in the last part of this explanation. Feasible region simply means what is the values, or what are the values of x and y that would satisfy each of these three inequalities. And of course, again, x being greater than or equal to 0 and y being greater than or equal to 0. Where would these conditions be met? Where the student works no more than 12 hours in the cafeteria and no more than 14 hours in the library, but must work at least, if not more, than 20 hours at both jobs. So let's have a look at how we're going to define that. In the next slide, I'm going to show you a graph and we'll plot the information that we need. So here we have a graph, x and y, and we are graphing, I'll just move it aside here. We're graphing those three inequalities. We're already working in the positive space, so bound by these two axes. But we have x is less than or equal to 12, and we have y is less than or equal to 14, and we have x plus y is greater than or equal to 20. Okay? So let's see how we're going to plot this. So what we're going to do is pretend it is an equality. So we're going to graph x equals 12 because she could work 12 hours in the cafeteria, 12 hours or less. X equals 12 is a vertical line stemming from the point 12, 0. So I guess first we need to label the axes. Of course, this is the origin at 0, 0. I'm going to maybe divide them up like this. So we would have 5, 10, 15, 20. Remember, we're dividing up the spaces equally. So 5, 10, 15, and 20, let's say. 5, 10, 15, and 20. And again, x equals 12 is a vertical line stemming from 12 and 0. So 12 about here, I guess. So we're going to draw a straight line up. Then we have y is less than or equal to 14. So we're going to graph y equals 14, which is a horizontal line stemming from 0 and 14. So I guess that's going to be over here. And I'm going to label them. This is x equals 12. This is y equals 14. And then we have this last one here to graph. X plus y is greater than or equal to 20. So what we do there is we're going to set up a t-table for graphing. So we're going to choose values of x and y. Remember, it's a straight line, so we only need 2 points, and I'm going to suggest the easiest ones are, what is the value of y when x is 0? Well, it's 20. What is the value of x when y is 0? Well, it's also 20. So we have 2 points on a line, 0 and 20, and 20 and 0. So let's plot the first one. 0 and 20 would be up here, and 20 and 0 would be over here. And now I'm going to have to draw a straight line between those two values. Let's see if I can do it. Nice. Okay, so now we've completed the picture here with our three inequalities graphed, and now we have to define that feasible region. Where is it feasible that this student can balance fewer than 12 hours in the cafeteria, fewer than 14 hours in the library, but meeting that cafeteria and library must be at least 20 hours or more. Okay, I'm just going to pick up another color here so I can demonstrate. So it has to be less than or equal to 14, y. So that's going to be spaces that are below that y equals 14 line, right? It has to be, the hours in the cafeteria have to be less than or equal to 12. So they're going to be on this side of that x equals 12 line, right? Okay. And x plus y have to be greater than or equal to 20, so it has to be above that inequality there. Yeah? Okay. So what we can see just by looking at these arrows is that it can't be in this space here because that is above y equals 14. It can't be in this space here because that is greater than the 12 hours in the cafeteria. It can't be in this space because it doesn't satisfy the x plus y is greater than 20. And it can't be here either because it is greater than x is 12. Okay, so here as well it can't be because it's less than x plus y is greater than or equal to 12, and here as well. So if we're going to look at the space where it is possible or feasible, we're looking at this space right in here. I'm shading it green. You can see that area shaded in green has values that are that would work for x plus y. Has to be greater than or equal to 20. It's above that cross line. It is less than y equals 14, so it satisfies that requirement that she work 14 hours or less at the library. And it also satisfies that x equals 12, where she has to work 12 or fewer hours in the cafeteria. So that would be the feasible region where each of these three inequalities are satisfied, or possible, or feasible. Okay? In the next couple of questions, we're going to look at matrices or matrix. A matrix is the singular form, matrix. And more than one matrix, we would say matrices. Yeah. Matrices are ways of giving information over. It really is the start or the basis of some linear programming to solve multiple equations through using linear programming. We're just going to learn the very basics of setting up a matrix and what things you can do with it. We're going to look at addition of matrices, subtraction, scalar multiplication, so scaling up or scaling down a matrix. And we're going to look at finding an average or division, right? Where we would divide by the number of matrices we have. Yeah. So if we look at a matrix, matrices can be defined by how many rows and how many columns they have, kind of like an Excel spreadsheet, really, when I think about it. And you can call a matrix by a row by the column. So say we have a matrix like this, 3, 2, 5. So in this case, we have 3 rows and 1 column. So we would have a 3 by 1 matrix. Now, what if we reverse those? What if we had 3, 2, 5? In this case now, we have 1 row and 3 columns. So we would have a 1 by 3 matrix. Okay? In order to add or subtract matrices, they have to be the same size. So they have to have the same number of rows and the same number of columns. If we can't, then we can't perform those operations. So let's look at our first question. Here we have a question about shipments to warehouses from a central location. So we have the September shipments of the 3 models of sofas and chairs from the Easy Life Company to the Toronto, Vancouver, and Calgary warehouses are given respectively in matrices as followed. So we have a 2x3 matrix for Toronto, 2x3 matrix for Vancouver, and a 2x3 matrix for Calgary. It says here, what was the total amount shipped to the 3 warehouses in September? So we see that total amount, of course, that means we're going to add them together, right? So we're going to add. In order to perform that operation, we need to ensure that the matrices are the same size, which indeed we just verified. And so we can go about our addition. So let me just make these a little bit bigger, I think. I'm going to use different colors to illustrate what we're adding together. Okay, so for the first one, I'll just use black pen. We're going to create, again, a matrix that is also 2 rows, 3 columns. So in the first one, we're going to add together the column 1, row 1, column 1, row 1, and column 1, row 1. We're going to add those together, and we find that they add to 97. Okay? Then the next one we would do is add the second column, row 1, second column, row 1, second column, row 1. And when we add those 3 values together, we get 92. And then we would go to the first row, third column, first row, third column. Those 3 circled in blue, we'd add those together. They add up to 86. Yeah, you get my point? We're adding up the values that are in the same position in the matrices. So that they add up to 139. Let's see if you can see the yellow. So the middle one, 40, 47, 34, second row, second column. They add to 121. And then I'll go back and use black again for the second row, third column. We're adding those again, 100. Okay, so this very colorful matrix, this one here, is the sum of the 3 shipments to the various warehouses, Toronto, Vancouver, and Calgary, and simply adding each of the values that occupy the same position in the matrices. This question I have borrowed from another resource, McGraw-Hill resource, because it did offer another comprehensive look at the use of matrices. The question reads, Ms. Fong and Mr. Petrus are salespeople for a new car agency that sells only 2 models of cars. August was the last month for this year's models, and next year's models were introduced in September. Gross dollar sales for each month are given in the following matrices. So you can see August sales, we have compact cars, luxury cars, and we have the 2 salespeople, Ms. Fong and Mr. Petrus. They're labeled Matrix A and Matrix B. And you can see, for example, Ms. Fong had $36,000 in compact sales in August, and Mr. Petrus had $216,000 in luxury car sales in September, right? So we can see those 2 values here and here. That's just pointing out where these values are. So part A says, what were the combined dollar values in August and September for each salesman and each model? I don't think I'm actually going to do the additions here, but I would say if we're combining the combined dollar sales, August and September, for each salesman and each model, that simply would mean we're going to add A plus B. So we would add 36,000 to 144,000. We would add 72,000 to 288,000, and so on. And we would have that combination matrix, that addition matrix. Okay. B, let's see what B is asking. It says, what was the increase in dollar sales from August to September? So in that case, we're looking for a difference between the two. How is one less than, or how is one greater than the other? So we're looking at how much the sales increased from September to from August. So in that case, we would be taking the September matrix and we would be subtracting the values in the A matrix to see what the increase was month over month. Yeah. So C, let's see. C says, if both salespeople receive a 3% commission on gross dollar sales, compute or calculate the commission for each salesperson for each model sold in September. So 3% commission, that's equivalent to 0.03. So, and it says for September, so that's the B matrix. So a 3% commission for each salesperson for each model sold in September. We would multiply, this is that scalar multiplication. We're going to multiply each of the values in matrix B by 0.03 to determine what the commissions were. Let's see about D. It says, what was the average sales over the months of August and September? So remember, average, we're dividing by the number of points we have, in this case the number of matrices we have. So we have two matrices, A and B. We already in A have that addition matrix, right? We've already added A plus B. So I would take the matrix that we have found in part A of this question and divide each of those values in that addition matrix divided by 2, because we're averaging those 2 months. Yeah, there's a lot we can do with matrices. They're very helpful tools. The last thing we're going to look at is something called optimization. Optimization comes from the root optimal, meaning to make the best possible decisions, or to have the best outcome. And often optimization is used to describe how a business might utilize its resources, whether it's human resources or materials and so forth, to ensure that there's the best outcome, whether it's saving money or whether it's increasing profit or maximizing profit or so on. So optimization is used to make the best decisions or make the best uses. So we can say that we would want to maximize profit or minimize costs or so on. But in this case, we're going to look at ways of utilizing resources in order to have the best outcome. So the first example we're going to look at involves supplying an office with filing cabinets. So in this case, an office manager needs to purchase new filing cabinets. He knows that ACE cabinets cost $40 each and require 6 square feet of floor space and hold 8 cubic feet of files. On the other hand, each Excello cabinet costs $80, requires 8 square feet of floor space, and holds 12 cubic feet of files. The budget allows for spending no more than $560, while the office has room for no more than 72 square feet of cabinets. The manager also wants the greatest storage capacity within the limitations imposed by the spending, the cost, and the space available. So in this case, and in the next one we're going to do, we are only looking at setting up the optimization equations, those things that we need to be aware of when we're when we're following these instructions, whether there's a money capacity or space capacity. So we're not actually going to solve the equations, but we're going to set them up, and then in theory we could send them to a computer in order to solve for the best possible outcome. So in this case, we have some information. The floor space, for example, imagine that is square feet, so a foot by foot on the ground. So that's how much space on the floor it occupies. That idea of capacity or volume, the 8 cubic feet and 12 cubic feet, that includes the length, the width, and the height, right, of this filing cabinet. And that optimization factor is capacity. So the manager wants the largest volume or capacity to hold files as possible. So in these kind of questions, it's easy to get muddled down in the words. So I would always translate what's there in words into a table, and then we can extract the equations from it. So the variables we have are the cost, right? So we have a cost. We have the space, the floor space, right, or area. And we have the volume. So space is area, right? So we have those three things. We have two types of filing cabinet, and we don't have to buy all or one. We don't have to buy all ACE or all Excello, so it's not an either or. But we're going to look at the ACE filing cabinets, and we're going to label the ACE ones X and the Excello Y. We'll use the variable Y. Okay. So we know from the question that ACE cabinets cost $40 each, and Excello cost $80. So if we were looking at just cost, then we could say, well, gee, Excello are twice as much money, so maybe we should go with that. However, they also have varying space or area they take up, and also a difference in capacity or volume, which is what we're looking for. The space the ACE filing cabinet takes up is 6 square feet, and the Excello is 8 square feet. So Excello takes up a little bit more space, and so that means they're either longer or wider, and so that could explain the higher price. The volume or the capacity were 8 cubic feet for the ACE filing cabinet and 12 for the Excello. So that's a great way to just organize your ideas. Now, we are told that we can only spend $560. So that's going to limit how much we can spend. We are limited by space, so we're only allowed to take up 72 square feet. And this is what we want to optimize or maximize, is that capacity or volume. And that's going to make up our Z function, Z being the thing that we're trying to optimize or maximize. So let's set up our equations, or actually inequalities. So in the first one, we have 40x plus 80y. So 40 times each ACE filing cabinet, 80 times each Excello filing cabinet, has to be less than or equal to $560. That's all the office manager says we have to spend. Okay? If we're looking at the space or the area, 6 square feet for the ACE filing cabinet and 8 square feet for the Excello, so plus 8y, has to be less than or equal to 72 square feet. That's all we have in the office, right? We have to be able to walk around and so on and so forth. The last thing then is the Z function. So Z is what we're trying to optimize. So we're going to say Z is equal to 8x plus 12y. Right? So those are our functions. And the last thing, of course, we have to remember is that x has to be greater than or equal to 0, and y has to be greater than or equal to 0 because we can't have negative filing cabinets. And a filing cabinet is either 0 or 1 or 2 or 3. Yeah, so we're going to put it that way. And that's it. That's all we have to do is set them up this way. Let's look at this optimization question where we have limited quantities of resources, in this case steel and aluminum, and we're trying to determine what the best use of these resources would be in order to make sure that we maximize our profit. Okay, so a bicycle manufacturer builds 1, 3, and 10 speed models of bikes. The bicycles need both aluminum and steel. The company has available 91,800 units of steel and 42,000 units of aluminum. The 1, 3, and 10 speed models need, respectively, so 20 units of steel, 30 units of steel, and 40 units of steel, and 12, 21, and 16 units of aluminum. The company makes $8 per 1-speed bike, $12 per 3-speed bike, and $24 per 10-speed bike. So we are asked to set up the optimization problem to optimize the profit with respect to production levels. So essentially we're saying how many 1-speed bikes, how many 3-speed, how many 10-speed bikes should be manufactured in order to ensure the most profit based on the resources that are available. So again, the best way to approach a question like this with a lot of words and a lot of numbers is set up a table so we can easily distinguish what we're looking for. So in this case, we have 1-speed bike, right? We have a 3-speed bike and we have a 10-speed bike. Okay. The resources we have are aluminum and steel. And of course, we also have profit, which is what we're trying to maximize or optimize. So again, we're going to address the variables, so x, y, and because we have 3 variables this time, we can't use z because the z function is our optimization function. So we'll use a w here for a 10-speed bike, okay? So the 1-speed bike requires 12 units of aluminum, 20 units of steel, and has a profit of $8. The 3-speed bike uses 21 units of steel, 21 units of aluminum, 30 units of steel, and has a profit of $12. The last one, the 10-speed bike, uses 16 units of aluminum, 40 units of steel, and has a profit of $24. Now, if we look at this data on its own, there's varying things, many variables involved. We can't directly say, oh, this is the best option, we should produce this or that. But we would be able to do that if we're solving these equations to determine where we should invest our resources. But what we're asked to do here is set up the optimization problem. So in this case, we have 42,000 units of aluminum available. We have 91,800 units of steel, and we're trying to maximize or optimize the profit. So that will be our Z function. So again, we're going to read down each of these columns and create these equations, the optimization problem. So we have 12x plus 21y plus 16w must be less than or equal to 42,000. So we're looking at how we're going to use the aluminum, that resource aluminum. The next one we're going to use is steel. So we have 20x plus 30y plus 40W, and that has to use less than or equal to 91,800 units of steel. That's all this manufacturer has. With respect to the profit now, that's our Z function or maximization function. The 1-speed bikes are $8 profit. The 3-speed is 12, and the 10-speed is 24. Yeah. And again, we can't have negative values of bicycles. You either have bikes or you don't. So X has to be greater than or equal to 0. Y has to be greater than or equal to 0. And W has to be greater than or equal to 0. Right? So we can have 0 1-speeds or some positive number. And the same for the other models. Yeah. So that's a great way to look at optimization and how to really pull the information out of a word problem into a table and then translate that into the optimization equations.